So one of the key things that you're going to have to be able to know and do is to use the definition of a derivative as a function in order to demonstrate that one of the differentiation methods that we use as shortcuts, why that works. We're going to start with differentiating a power function. And essentially what we're going to try to show is why, if f of x equals x to the n, f prime of x is equal to n times x to the n minus 1. We want to be able to show why that works. It's a very useful property, but it helps us to understand that everything we do is going to fit together in some way. Before I get to that, we need to do a little bit of a review of how to expand a binomial expression, namely x plus h to the n. I'd like to start by reminding you that you can do a binomial expansion by use of Pascal's triangle. If you don't remember what that looks like, you're going to want to write this down. So remember, Pascal's triangle starts with a trio of ones. Then, to produce successive parts of this table, we're always going to start each one with a 1 placed just to the left of the one above it. And then we're going to add 2 entries together to make the next entry and end our row with a 1. Each row is going to be 1 unit or 1 term larger than the one above it. So as you can see here, I'm just starting my row with a 1. I'm adding together elements and putting in a 1 on the other end as well. What I'm going to do for the purposes of this demonstration is show you all of the values of the table that you're going to need. If you're unfamiliar with this table, or you just want to have it for reference for our future discussions, I would stop the video for just a minute and write this table down. All right, assuming that you have what you need from the table, we're now going to look at 3 examples of binomial expansion and how we use that information to get there. We're going to start by saying, what if we have plain old x plus 4, and we want to raise that to the 4th power? How would I use binomial expansion to do this? Well, since I have x plus 4, I could make a series of rectangular boxes to do this expansion. I could use foil. It's going to get pretty heavy and sticky pretty quickly. So instead, we're going to use binomial expansion. The first thing I'm going to do is start with the relevant row of Pascal's triangle, and that row has these digits on it: a 1, a 4, a 6, another 4, and a 1. Those are going to become the coefficients of each term of the expansion. I also know that the expansion comes in a certain pattern. So for example, I'm going to start by writing those coefficients, and then I'm going to leave some space for what I'm going to do in each of the subsequent terms. Okay. Now, the next thing we're going to notice is that if we've done these types of expansions before, we know that we're going to start with x. It's going to appear with different exponents in each part of the expansion. It's going to start, but we know there's going to be a term where we've multiplied x by itself 4 times, so there'll be an x to the 4th term. The next one will be an x to the 3rd, x to the 2nd, x to the 1st, and then x to the 0, which of course we know is 1. Additionally, we're going to take the 4, which is the other half of the binomial term, and it's going to appear in each of the 4 terms, and we're going to flip-flop the order here. So we're going to have a term where 4 actually doesn't appear because it's represented by 4 to the 0, then 4 to the 1st, the 2nd, the 3rd, and the 4th. By looking at it this way, we can notice some parts of the pattern aren't as useful as others. For example, we're always going to have a 1 coefficient on the first term and the last term. We're not always going to write that, but it's going to be there. We also know that we're going to have 4 to the 0 on the first term and x to the 0 on the last term. So those aren't very useful either. What we're going to try to do now is just simplify what we have. The first term, since we have 2 parts that aren't very important, we're going to write x to the 4th to represent that. That's really the only part that matters. It's right here. Plus, in the second term, we're going to have this first 4 times the back 4, which is going to give us 16x to the 3rd, plus We're going to have a 6 times a 16, that's going to be 96 x to the second. We're going to have a 4 times a 4 to the third, that's going to be 4 to the fourth, which is 256 x. And on the last term, remember that the first part and the last part we've decided, or that the x to the 0 and the 1 are not that important. So we're going to just be left with 4 to the fourth, which is 256. This is the same as the expansion of x plus 4 to the fourth. Now you might wonder, okay, what happens if I switch from, say, x plus 4 to the fourth to x minus 4 to the fourth? There's good news. The good news is all the terms will stay exactly the same, but some of the terms will be negative. Now you could do this whole expansion out the longhand way to verify this, but the good news is we could expand this just like we had before. We have the same exact terms, except the only thing that's going to change is that the signs are going to alternate from positive to negative. Here's a negative, and then here's a positive and a positive. That's nice to know, and if we wrote out the expansion, you would see that on the terms that become negative, if we think of the back end of this as not just 4 but negative 4, when we raise that to an odd exponent, it's going to make the expansion term negative. Let's try one harder one just to see how it works. So let's say we had something like 2x minus 3 to the 5th power. So the relevant row of Pascal's triangle looks like this. 1, 5, 10, another 10, a 5, and a 1. So what we're going to do is start each term with those values. So here's 1, put some parentheses here and here. A 5, parentheses, a 10, parentheses, another 10, a 5, and a 1. So we have 6 terms this time. The first term, or the first part of that term, is going to be the 2 x's, and notice it's 2x, don't keep that 2 separate. So I'll put a 2x in the front side of each one of these parentheses. And I'm going to carefully, instead of just putting 3, I'm going to put negative 3, because that's really what we have going on. Now we just need to add some exponents. So remember that the first term, the leading term, the 2x, is going to start out to the 5th power, then to the 4th, then to the 3rd, the 2nd, the 1st, and the 0. The other terms, the negative 3's, are going to go in exactly the opposite order. The other thing you might want to notice, if I were to add the 2 exponents from each term of the expansion, I always get 5. 5 plus 0, 5. 4 plus 1, 5. 3 plus 2, 5, and so forth. Now all I have to do is actually do the arithmetic to do the expansion here. You could stop the video for just a minute and do that, and I'm going to write the answer, and you can check your work. So here's the solution at the bottom of the screen, and you can see that the numbers can get quite large quite quickly because you're talking about powers of 2 and powers of 3 and multiplying those together. So now that we've seen how this expansion works, let's see what we're going to do with it. What we're going to try to do here is we're going to take a very simple version, in this case f of x equals x to the 4th, and we're going to try to use the definition of derivative to show what its derivative should be. We know what we're expecting. We're expecting that f prime of x is going to be 4 times x to the 3rd, but we'd like to see how that works and why it works. So the first thing we need to remember is what the definition of derivative says. It says that f prime of x is the limit, and I'm going to use the h form of this because I think it's a little easier. The limit is h goes to 0 of f of x plus h minus f of x over h. So what we're going to have to do is actually calculate that for this particular function. So we're going to say this is equal to the limit, because we haven't taken it yet, so we keep writing limit over and over again, of what? Well, we have to plug x plus h into the function. So that's going to look like x plus h to the fourth minus x to the fourth over h. Now you can see why we spent the time on the binomial expansion, because we're going to need to expand the expression at the top. If we tried to evaluate it right now, we would put a 0 in for h and get 0 in the denominator. We'd put 0 in for h in the numerator and get x to the fourth minus x to the fourth. We'd have indeterminate form. So we're going to do an expansion of the numerator and hope that something will cancel. So, using what we just saw, we're going to have to use the row of Pascal's triangle that uses the coefficients 1, 4, 6, 4, and 1. So we know we're going to have 1 times x to the fourth. We also know that we're going to have, added onto that, a 4 times x to the third times h to the first, plus we're going to have, the next term is going to start with a 6 times x squared times h squared, plus the next term is going to start with a 4, x h to the third, and then the last term is going to be 1 times h to the fourth. Now we still have to remember minus x to the fourth, because that's still there. It's here at the end of the expression at the top. And we're going to divide that by h. Now if you'll notice, a number of these terms have h's in them, and then there's also two terms that are going to just cancel. Let's see where those are. We have an x to the fourth at the very beginning, minus an x to the fourth at the end. Those are going to cancel out. Okay? Notice everything else has at least one h in it. We have an h here, we have an h here, here, and here. Because of that, we're going to factor out an h. And the only reason I really want to write this step out is a lot of people do not cancel this properly. Let's see what we got left. We could factor out an h and be left with 4x cubed plus 6x squared and another h. There'd still be an h there. So this leading h times the h on the inside would give us h squared back, plus 4x h squared plus h cubed. And that's over h. Now, my h's, the one on the outside and this one down here, will cancel. And I'm going to have left the limit as h approaches 0 of, now I'm not using a fraction, 4x cubed plus 6x squared h plus 4x h squared plus h to the third. Now let's see what happens if we take the limit as h approaches 0. Well, h is going to approach 0. I'm going to have 0 in this term. That's going to cancel out. This term's going to do the same thing because it's going to go to 0 if I put a 0 in for h. This term will do the same thing. The only thing I'm going to have left is this. But remember at the top, that's what we were expecting, right here. So that means that this limit as h approaches 0 is simply 4x cubed, and that's f prime of x. You need to be prepared to do this for a simple function like this one on a class assessment. So I would take a moment if you need to, pause the page, take notes on the process, or repeat it and watch it one more time. But essentially that's what you're going to have to do.